All right, recorded is rolling. It is Wednesday, Hold on, let's pause it. All right, Wednesday, September 14th. Here's the agenda for today. All right, so yesterday you guys had a spring scale lab up here at the top class. Pretty soon I'll go over the ideal answers with you guys, but I got a couple things we need to do for that. Okay, well, here's some other things I want to go over. All right, guys, tomorrow's going to be a weird day, and I can't tell you exactly how, because there's going to be testing in this room for periods 1 through 3. So we're going to be relocated somewhere else. Where that is, I don't know. This is all just being handed to us last minute through email. So I don't have those details yet, but I'll have to post something either on my door or outside in the hallway to tell you guys where you guys are supposed to go. I think I'll be with you guys. I'm pretty sure I'm not proctoring, but I'm not even 100% sure on that. So time will tell. If I am with you guys tomorrow, we'll be in some other room. We're going to find out. And my plan is to do a 2-part Christian lab with you guys tomorrow. So yeah, hopefully by the end of class today, I'll at least have you guys set up with that. But we'll see. Yeah, sort of a plan in my mind, but we'll have to get the details on how it's going to work out. All right. So before we go into physics stuff, I got in my teacher mailbox this morning this Teacher of the Year ballot. And what I've always done for last 10 years is, well, I always ask my students who I should check the box for. So there's some nominations for Teacher of the Year. Every teacher, here, guys, look up here. Guys, on. Right, so every teacher receives one of these ballots in their box, and then they just vote on Teacher of the Year and also Employee of the Year. But since I don't know what the other teachers like that you guys do, I always pull my students to say, okay, well, what box should I check? Sort of like an electoral college type system. And so here we got these nominations, and I always also I always take this opportunity to teach students about ranked choice voting. I've done this for like 10 years now. I've done it for 10 years, and I know it's like just come up in the news. It's like it's one of those issues that's like starting to finally become part of public consciousness. People are starting to. It's a procedure of a democracy. It's like one way to run an election system. It actually has some advantages over first past the post voting. So I will walk you guys through a simulation of how that works. Do you guys have like some paper out on your desk? Yeah, maybe your notes, maybe that lab page, just on paper. Now you're not going to turn this in, but we're gonna run a simulation of what ranked choice voting is. Yeah, blank paper, go for it. All right. So we got 4 nominations here. We got Miss Sherritt, we got Miss Hudkins, we got Mr. Clubs, and Miss Velasquez. All right, so what you're gonna do on your paper. Now, again, not picking this up. This is we're gonna do an activity with us though. Right? Is go ahead and rank those according those teachers according to like put it number 1 next to who you think you really would like to see be Teacher of the Year out of those options. Right? Again, I don't have a stake in this. I have no idea who's better or what. I have no idea myself, but you guys probably have some idea. Right? Put in number 2 next to your number 2 choice. Put in number 3 next to your number 3 choice. Okay, you guys can do that. And if you only know 2 of those 4, you can just rank 2 and then just stop ranking. You could always do that. You're like, oh, okay, rank 1, rank 2, and then I just don't care after that. You can do that too. No. Yeah. What's that? Oh, okay. Yeah. If you don't know any of them and you don't really care, then well, you don't have to vote. So that's all right. Or if you just want to make up something for fun, you can make up something for fun. Right? Yeah, I guess that's true too. If you want to participate in the spring sports activity, just to see how it plays out, but you have no idea who any of those teachers are, you can just like randomize it and then by probability statistics, and they kind of even out. Okay. All right, guys read this for? Let's figure out how you want it. Who needs more time? Okay, yeah. Give you guys one more time here. All right, so we got Sherritt, Hudkins, Clubs, and Velasquez. put 1 next to your number 1 choice, a 2 next to your number 2 choice, 3 next to your number 3 choice. Okay.
I was having a great time. You don't want to see your finger.
All right, so you guys about ready now? All right, so what do we do? Oh, so just look at your number 1 ranking choice. Okay. All right, so we got Sheritot, Hudkins, that's ready. Club and Velasquez. All right, so we're gonna do a show of hands just to do a kind of top version of this. All right, so show of hands. Who ranked Miss Sheritot as their number 1? Who's got Miss Sheritot as their number 1? Right, hold your hand up. I'm gonna do a count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we got 11 votes on Sheritot. Right. Who voted for Miss Hudkins as their number 1? Right, we got 1, 2, 3, 4, 5, 6. So 6 for Hudkins. Right. Who voted for Mr. Klebs, number 1? Mr. Klebs got 1, 2, 3, 4, 5, 6, 7. Got 7 on Klebs. Who voted for Miss Velasquez, number 1? Got 1, 2, 3, 4. So okay, looks like 4 on Velasquez. All right. Oh, sorry. Let me zoom out so you guys can see better. Okay. So there we go. There's how the voting would end up according to your number 1 votes. Now there's different kinds of voting procedures you can use. There's a lot of them, but I want to sort of narrow it down to kind of 2 systems just to move things along and plant some ideas in your mind. Although if you find it's really interesting, you can go on the internet and find all different kinds of voting systems. But let's compare a first past the post to we're going to do a particular version of ranked choice called instant runoff voting. It's not the only way you can process ranked choice, but we're going to do this around. Okay. So first past the post, this is just whoever has the most votes wins. And this is the system that is most commonly used in the state. And of course, every state runs their own elections, but that's what's been used like forever, right? Whoever gets the most votes wins, right? So by this system, first past the post, who wins that race? What do you think? Yeah, sure, Todd. Right. Hey, who has the majority? Wait, are you sure?
Anyone else?
No one has the majority.
No one. Yeah, gotcha. Yeah, no one has the majority, right? Because what's majority? Majority is like more than half, right? Right. Now here's where let's do a little abstraction, right? Let's say that you use like in like a political system, like in a democracy, usually candidates represent some kind of like platform, right? Let's just suppose that like Sheritot was like one end of the spectrum and some political spectrum, and these other 3 candidates were sort of bunched together on like the other side. Right? Do you guys see how like these 3 candidates would be like well, we're trying to introduce an idea called the spoiler effect. So they like spoiling the election, right? So if you just went by who had the most votes, this would be called the plurality. Like Ms. Sheritot has the plurality. She would win the election, even though most people probably would have preferred somebody else. Right? You guys get it? Right. So so this sets up a system where you get situations like minority rule, like most voters aren't happy with who won the election because they really wanted like somebody else. And then it sets into a place like strategic voting. So then you don't really vote for who you're interested in. You vote for, well, how is everybody else voting? And now I have to change how I'm voting based on how I think everybody else is going to vote based on polls. Maybe candidates have to drop out of the race just so they don't spoil the election for like their own platform and their own interests. Like, maybe they have some interest in, but there's some other candidate has pretty similar platforms. Say, okay, well, I don't want to divert votes away from them. Right. So, yes. So what we can do is we can take advantage of the fact that you guys ranked your votes, and now we have actually more data, and we don't have to go with a straight plurality. We can actually try to achieve a majority. Right. So now here's where there's different ways you can do this, and let's look at instant runoff voting. Instant runoff voting, what you do is you eliminate the candidate with the least number of votes. So in this case, Velasquez, not gonna make it. Right. And then, how many totals here? 17, 24, 26, 28. All right. All right. And then what I would do is find the four people who's ranked Velasquez as their number one and say, okay, well, who was their second choice, right? So let's sort of simulate that. What we're gonna do is we're gonna do a complete rerun, but in theory, I would be like looking at your guys' ballots, right? All right, so let's have a revote. All right, so who's voting for share? So you only get 2 choices now, right? You guys get that? Okay. Who's voting for a share tap? Who's voting for share tap? It's we got 1, 2, 3, 4, 5, 6, 7, 8. It went down. Okay, that makes no sense, but whatever. All right, who's voting for Hudgens? Hudgens. We got 1, 2, 3, 4, 5. Okay, well, somebody else. Oh, you're gonna throw a vote on straight hat? All right, I mean, in theory, it should be at least 11 and at least 6, but okay, whatever. All right, who's voting for clubs? Who's voting for clubs? All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so now, well, okay.
We're testing your
In,
system.
in theory, no, okay, guys. The reason I had you write it down on paper is because you're supposed to be like a computer system. You're just following on your paper. If you voted for one of these 3 first, you're just continuing to vote for that person. If you vote for Velasquez first, well, now you can't vote for Velasquez. Now you're changing your vote, right? But see, guys, if you guys handed in your papers and we actually did this like the full proper way, it would take all class period. So I'm trying to do like a fast version of this, right? But anyway, we'll go with these numbers. All right, so now the person with the least number of votes is Hudgens. So Hudgens gets eliminated from the race, right? And now it's just down to either Sharecat or clubs, right? You guys see that? Right. But now you see how we're gonna force a majority. Like at the end of this process, there will be a majority. Right. Now there are different ways to get there, and the way we did with this instant runout process that happened to narrow down to these 2 candidates, right? All right, so you either get to vote for Sharecat or clubs, right? You guys clear on that? Right? All right, so vote for Sharecat. He's voting for Sharecat. I got 1, 2, 3, 4, 5, 6, 7, 8, 9.
Good job, guys.
All right. Who's voting for clubs? Vote for clubs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right. All right. So now at this point in the race, who has the majority? Clubs. And that actually at this point is a true majority, right? It's like a true, like undeniable majority at this point. Okay.
I think Mr. Griffin
Right.
should be.
So I will pull my other classes. We'll do the same activity, but I'll say, okay, for my first period class, I know that they chose clubs, so hold on to that idea, and I'll see what my other class come up with, and there you go. Right. Who has any questions about that ranked choice process, that instant runout process?
Don't they do that in Australia?
I don't know. Possibly, yeah.
They do it in Alaska.
Yeah. All right. So next deal, I've got a challenge cup for you guys. All right, so you guys see this Frankenstein conglomeration of a cup, all hot glued together. All right, so there's at least 2 cups glued together here. There's something weird going on. And do you guys see like a straw hole down the bottom there? You guys see that? All right. And if I turn this around, I see on the other side there's a straw hole here too. Okay. So to mock up some kind of schematic, what's going on? All right.
Well, you could still get it in.
Yeah, some kind of cups going on. All right. Like nested each other somehow. All right. I see like a straw hole here. I see a straw hole here. Right. You guys basically see that, right? All right. And I'm gonna fill this up. Start with water. Should have done a trial run this morning. Ooh, all right. I think it's gonna work. All right. So you guys see a pathway filled with water. All right, so there's a story with this. This actually goes back thousands of years ago. I invite some guests over, pour some water, and then they say, "Give me more water." So you guys do see it's filled halfway with water. It's actually holding the water, right? So at this point, the schematic is filled halfway with water. Right? It's functioning just as a normal cup. Everything's all fine and good, right? Now I fill this to the brim, and then now it's all pouring out the bottom. There, let me just for the video, get a quick shot of this. Right. So yeah, if you're watching this on the video, oh look at that. Oh, it's all pouring out. All right. Now, right, let's reset here. Right. This is draining extremely slowly. I'm gonna let it drain. There's gonna be no tricks to this. This is just taking longer than it should. Right. It's probably some like dust cake in there. I'm just gonna leave this right here to let it drain. Right. But I can tell you what's gonna happen, and I'll prove it to you guys after that thing drains. Which is here. I filled this all the way to the top with water. Right, and then starts pouring out, right? Starts pouring out, right? But the water level is not going to go back to the previous water level. Actually, the entire cup is going to drain. The entire cup's going to drain. It's getting pretty close. It's down below the level it was originally at. I'm just watching it. Okay. Ooh, I think this is the last dregs right here. Oh yeah, thank you. Yeah. Oh, that actually worked really well. All right. Yeah, thank you. Right. And let's take a look. Look at that. I mean, there's a little bit of dregs of water left, but it's basically empty, isn't it? Okay. So just to recap what you guys just saw. This cup is a straw hole here, right? But we don't know exactly what's going on. What's the mechanism? How are the straws connected between those two cups? Right? I fill it halfway with water. The water stays in the cup. Functions perfectly normal as a cup. I fill it all the way top, and it starts draining out the bottom, but it doesn't just drain back to the previous level. In fact, the entire cup drains. Okay? So, challenge question for you guys is: how are these straws connected on the inside? I'm gonna give you guys at least a day to think about that. Right? How are those straws connected on the inside? Or I don't know. Does anybody happen to know the answer right away? Yeah.
This kind of where it like goes down and then the elbow.
Here, if you were to draw that, what would you draw like?
I was gonna say that. You guys see that?
All right, I will let you guys think about that. Yeah, you guys get to think about that for a while. All right, so you guys got all the Springtail labs from yesterday. All right, so remember, you guys have one of these per team. I want you guys to have that in front of you so that as we go over the ideal solutions, what I want you guys to get out of this, you'll be able to see exactly what you got and see whether you got the answer right or not. And I'll have you guys turn this in at the end of class. All right, so I did get my hands on some of these brown spring scales, which I only had one of yesterday, but these are ideal because they have kind of a medium stiffness spring. Right, remember yesterday with Hook's Law, I think it was KX, the whole deal. Right. And so this first one was real straightforward, just pick different masses and then weigh them. So I'm just going to make up some numbers that would work out pretty well ideal. So your guys' lab masses, one of them was like 100 grams. You had a 200 gram, you had a 500 gram, and there was a 1 kilogram, which is like 1,000 grams, right? And the numbers were stamped into the lab weight. So right here I have a 1 kilogram. This says 1,000 for, and then over here grams, 1,000 grams is this guy, right? Now, if you weigh those, here, let's do this one right here. This 1,000 grams. Now, 1,000 grams is a mass. Guys, if I take this up into space and it's floating around, is it still 1,000 grams of mass? Yes, it is. Right? Now, that's a different concept from weight. Weight is the gravity force pulling it down. Right? Let's see what the weight is measured in newtons. You can measure weight in newtons, right? Because weight's a force. And I'm going to stop this and then just turn it so the camera can see. Right? It's at 10 newtons. It happens to pretty well max out this Brown scale. Technically, this guy is 9.8 newtons, but I might just call it 10 newtons more often than not. Right. So, and you guys had some not super accurate scales yesterday anyway. You guys were trying to work with the right one. So, whoops, that's down here. 10 newtons. Okay. Hey, if 1,000 grams was 10 newtons, what do you think 100 grams was? 1 Newton. Yeah, 0.98, but let's call it 1 Newton. Pretty close to. Okay. This guy would have been close to 2 newtons. This guy was about 5 newtons. Right. And so this graph, if you have force in newtons on this axis and mass and grams on this axis, do you guys think all the points should line up like in a straight line like this? Right? Is that true? In fact, you can make an equation out of this that says weight is equal to the mass times the gravity field, right? Okay, so the weight is equal to mass times gravity field. In fact, a lot of times I'll express weight is just mg, right? Mass times gravity field. Okay, okay, guys, go with that. All right, next one. I want you guys to take a couple of spring scales, so I got newtons on the same side here, right? And lift one mass, but then adjust them so that maybe the weight distributes a little bit more on one or the other. Okay. Now, if this thing weighs about 10 newtons, let's say this is like a 1 kilogram mass, right, weighs about 10 newtons. If you distribute it evenly, do you think it'd be like 5 newtons and 5 newtons, right? Which would total to 10 newtons, right? What if you shift them a little bit so that one guy carries 7 newtons? What would the other one carry? 3 newtons? That's what you guys got for a total of 10 newtons, right? What if you put like 9 newtons on one side? What's the other side? 1. Right. So you guys definitely see the pattern, right? What if I put 2 on the side? 8. Right. Right. So it looks like the total number of newtons have to add up to 10, right? Let me introduce you guys a really important concept called here. I think I wrote it right here. Free body diagrams, abbreviated FBD. It's gonna be a really big concept this class. So free body diagram, what you're doing is you're just labeling all the forces on some object or like some point. Okay. Let's take a look at this point where these 3 objects are together: the spring skeleton and the lab mass. Okay. Okay. We'll do a bunch of free body diagrams, so this will be just a real brief one here. Right. I might say that there are like 10 newtons straight down, like 10 newtons of gravity force. That's weight. Okay. And then at this point, and what AP always wants you to do is like draw a dot and then draw a force vector succeeding from that. Okay. I've got so many newtons acting up here and so many newtons acting up here. So maybe this is like 6 newtons. This could be like 4 newtons. Okay, you guys get it? Okay. You guys see it? Those are vectors because force is a vector, and the length of the arrow vector is proportional to the force. Okay. So if I add this 6 to this 4, it balances out with this 10 down. Okay. I bet you guys can see now, if it's 10 newtons total up and 10 newtons down, that's a net force of what on this point? 0, right? 0. Right. If you have 0 net force, that's gonna be a situation called equilibrium. Right? Equilibrium, there's no net force, there's gonna be no accelerations, right? Which might be at rest, or it might be moving at constant velocity. In this case, might be at rest. Right. What does the graph look like?
Line with the negative slope.
Yeah, line with the negative slope, right? So if you have like, 5, 5 could be out here. You might have 7, 3 might be about here. See 9, 1 is probably about here. And then what, 2, 8, probably somewhere up here. Yeah, you should have got like a straight line with negative slope, just like that. All right, you guys got that? Yeah. Okay. Yeah, so there's 3 forces going on here. There's one force that just is the weight, right? And it's the same force over and over. So like a 10 newton force. Okay. And then there's the 2 spring scales pulling up. And if the net force is 0, right? And the way I might write that is like the sum of the forces is 0 newtons, right? The net force is 0 because it's just like at rest, that would be 0 newtons. Okay. Then the 2 up have to balance with the 10 newton down. Right? So it could be 6 and 4, it could be 7 and 3, it could be 5 and 5, right? But they have to add up to 10, right? The 2 spring scales have to add up to 10 to balance out the 10 down. Okay. Now, if I plot these like XY coordinates, like 5, yeah, they both pull it up. All right. Okay, so you got that? All right. Yeah, so there you go. Right. If I plot these like coordinates, like XY coordinates, then yeah, they will give like an inverse looking relationship there. Straight line down, negative slope. Right. This one, number 3. Now, this one we're about to do here is like hugely critically important. Because this takes forces into 2 dimensions. So I wanted you guys to actually maybe just, I've got a very small confined space here. Maybe just skip this bottom 3 scale and just focus on those top 2 especially. Right. That was the real important takeaway, is what's going on with the top 2. So I hook these top 2, right? And then if I distribute the weight evenly, it might be like 5 and 5. So here, let's say this is like a 1 kilogram mass down here, 1 kilogram. Right? When this bottom spring read 10 newtons And you think for every single one of these situations, the bottom spring was reading about 10 newtons, you guys think? Right. So I'll go ahead and do 10 newtons all the way down, regardless of the scenario. Right. Now each top spring, now this is like it, as long as it's evenly distributed, so it's like symmetrical, right? You guys see how it's like you make like a Y shape and then closer to a T, right? It might be like 5 and 5, so if you like say 5 newtons and 5 newtons, right? Which really starts out looking like the previous example, right? So, right. Now that's 0 degrees with respect to the vertical. See down here, I gave you guys the diagram. There's this dashed vertical line. I'm saying as you're making a shape that's closer and closer to a T shape, this is almost getting approaching a T, right? You guys see this angle here is approaching 90 degrees, right? So let me throw in some angles. Let's go like, say 30 degrees, 60 degrees, and like 80 degrees, for example, maybe something like that. Okay. Now what would the spring scale readings be? Okay. Now here's where you had to break out the protractor and figure out how to use the protractor. Now see this point where it's like all 3 lines come together, you got this line this way, this line this way, this line this way, they all kind of come together at this point, right? So you put the node of the protractor right there, you zero out this vertical line, and then you sweep out, well, one of these numbers of degrees, okay? So let me just see if I can fit it right here, so the camera can kind of see what's going on. There's about 30 degrees to the vertical. Okay. Here's like 0 degrees. So right now the spring scales are rating 5 and 5, like 5 newtons and 5 newtons. If I spread them out a little bit, it bumps up a little bit, but not very much. It's like 5.5, 5.5, maybe something like that. Just like 5.5 each. Okay, so it went up a little bit. That's kind of interesting. Okay, if I take this all the way up to 60 degrees from the vertical, right? Wouldn't that be exactly symmetrical? Like there'd be 120 degrees here, 120 degrees here, and 120 degrees between these two. Wouldn't that be the case? Right? Huh. And that's going to be actually a very interesting situation. Let me get it to that point. I'll do my best yet. All right, that point right, that's pretty close right there. It pretty well maxes out these scales. It's like 10, 10, and 10. So I'll put like 10 newtons here, like 10 each, right? And if I make that angle, that top angle any wider, right? Like let's say I try to like make a T shape with these, it goes beyond the scales, right? Now it's stretching even further than they're able to read. I'd have to break out the red or the white scales to get those readings, right? So it's just something bigger. I'm just gonna make up something just to roll with this, right? It's just gonna be larger than the actual weight itself, right? So if you start to plot this on this graph, again, what's the force of each top spring as a function of this angle, right? So at 0 degrees, each top spring was like 5 newtons. So this would be in newtons, this would be 5, right? At a 30-degree angle, it went up a little bit, not a whole lot, but it went up a little bit. At a 60-degree angle, that was a critically important angle. I definitely want to have that one there. That was where it's like a perfect, like symmetrical Y shape, right? It happened to exactly match the weight that it was holding, right? So it's like 10 off this way, 10 off this way, 10 down, right? And then if you did anything beyond that, it was only larger, right? Oh, guys see this curve here? You guys get something that looks kind of like that, right? In fact, if you try to make a perfect T, wouldn't that angle go to 90 degrees, right? Which is like how that maxes out this graph right here, right? Do you guys think that you can theoretically even make a perfect T? Well, you know what? I might be kind of overdue here to draw out this free body diagram with you guys. Right, let's look at this free body diagram. Right. So there's this point where all the spring scales come together. Right. We got one spring scale that's acting straight down. Right. We got one spring scale that's acting kind of, get the angle as best as I can get it, kind of that way. One spring scale is acting kind of this way, like that, right? Okay. Now, I tried to draw it the best I could. You guys see this is 120 degrees, 120 degrees, 120 degrees. Is that or relative to this dashed vertical line? It's kind of imaginary there. This would be 60 degrees. Is that right? Now, if this is 10 newtons, and let's just start from knowing what the answer is empirically, just having read it straight off the spring scale. This is 10 newtons, and this is 10 newtons. Right? Would that be true? Right. Now, we made a whole deal in this class about trigonometry and vectors. Like, this is some of the warm-up stuff we did, right? I covered algebra and trigonometry with you guys, like first week or two school. Okay. So we're going to align everything to a coordinate system that's aligned with gravity, right? Which includes this vertical axis that I drew on the page for you guys. And so we'll go vertical, horizontal. Guys, yeah. Now the weight is actually already aligned to that coordinate system. You guys, that. Okay. So I'm going to have to break these guys into components. So the one pulling up and to the left, well, it's kind of up and kind of to the left. So kind of upish, kind of to the left. Right. Notice I dashed those vectors, the vector components, I should say. See how I dashed them? Because if I made them solid, I would be like double representing them, saying like those are extra vectors. No, I'm just trying to re-represent this to newtons in terms of how much up and how much to the left. The same thing over here. This one is like how much up, how much to the right. Because it's kind of pulling up and to the right. Right? I wonder if we could quantify how much. If only we knew the angle. Oh, wait, we do know the angle. Isn't this right here 60 degrees? If it's all symmetrical, 60 degrees. Is that true? Right? Is that true? Okay. All right. So, I see some right triangles going on here. See some right triangles. I mean, that's what, anytime you have vector components, you're going to have some right triangles, right? Okay. And the hypotenuse is the measured value of 10 newtons. We read that straight off the spring scale. You guys did it yesterday. I just did it in front of you right now. Okay. If this is 60-degree angle, guys, what is this right here equal to? What times what? Yeah, 10 newtons times sine of 60 degrees. Right. Are you guys getting like about 8.6 something newtons? I think that's what it is, right? Is that what it is? 10 sine 60 degrees. Yeah, 8.66 newtons. Right. Now that's to the right. Oh, do you think this is also 8.66 newtons, but it's just to the left? Okay, I might even throw a negative sign on it, just say to the left. Okay. Hey, what about how much each of these guys is pulling strictly up? What is that?
10 times cosine.
10 times cosine is 60 degrees. And what is 10 newtons times cosine of 60 degrees? What is that? Flipping a cosine? 5, exactly, like 5.0 on the, because, you guys remember either cosine of 60 degrees or sine of 30 degrees, if you bounce off opposite of this one, is exactly 1/2 ratio. Is that? 5 newtons. So this is 5 newtons here, 5 newtons, and this is 5 newtons here. Right. So they're each pulling up with 5 newtons. You get that? Here's where it all comes together. You guys see 5 up and 5 up balances with this 10 down. You guys see that? Right? You guys see it? Right. Now, do you think if I change the angle from 60 degrees to like anything else, that the vertical forces are always going to balance? Right? I bet you could sort of figure out. Here, let's see how close I was on. I just kind of eyeballed this one. I think it was off a little bit. We're going to see how off I was on this one with a 30-degree angle. You guys think we can calculate that? Right. Let's do this from scratch. Right. Let's go 10 newtons down. Okay. See if you guys can stay a step ahead of me with this. Stay a step ahead of me. What if there's just like a 30-degree angle here? This one's pulling up with so many newtons. This one's pulling up to the right. Okay. And let's throw in a 30-degree angle right there. Okay. I'm going to break these into components a little bit differently from before. I'll go to the right, left first, and then up. It's easier to, I got more space for writing with ink about that. Right. So that would make this angle down here 60 degrees then, right? If you like that, or 30 degrees here. A little geometry, right? Okay. I wonder what these forces should have been. Right? Let's calculate. Let's get an exact ideal number. Okay. So whatever this force is, maybe I'll call it F sub t, like a tension force. Couldn't I say that tension force times how about cosine of 30 degrees would be up, right? So this is Ft times cosine of 30 degrees. Isn't that what that would be? You guys get? Okay. And this one's the exact same thing, right? As long as it's symmetrical. This is Ft, this is Ft, right? So this is Ft cosine 30 degrees, right? Is that true? Okay. All right. So if I add those two going up, they should exactly balance out with the 10 newtons down. Now we can set up an equation. Guess it? We can set up an equation. Okay. So that plus that's like 2 times the Ft cosine 30 degrees. You guys see 2 times because that plus that is like 2 of those. Okay. That has to be 10 newtons of force. Right? So if I take 10 newtons divide down this 2, and then divide down the cosine of 30 degrees. I'm getting tension force should have been ideally 5.77 newtons. Right? That's the ideal answer. Now, what did I say it was? I said it was, oh, actually, I was really close. I didn't know, but I said 5.5 newtons. Yeah, that's really close to like 5.77. Okay, guys, yeah. All right, so that actually worked out pretty good. All right, guys got on that so far? All right, now, there's still a couple of questions down here, and if you guys have really been following what I've been showing you guys so far, let me go back to the original one. Okay, I think you guys can get this next question. Can you ever make a perfect T shape? But can this angle go to perfect 90 and these pull exactly horizontally? Can that ever happen? No. Why not?
There's no upward force.
Yeah, you need some kind of upward force. In fact, these components are always going to be 5 and 5, aren't they? Right? They're 5 and 5 here. Over here, well, they would have worked out to here. I bet if you do 5.77 times cosine 30, I bet this is 5, and this is also 5 newtons, right? Right? Doesn't there always have to be an upward component to the force? Right? Yeah, so give these questions. As this angle approaches 90 degrees, let's say it approaches a perfect T shape. What is the tension in each of these spring scales approaching? Infinity. Infinity. That's the answer I was looking for. It would become infinite. Ah, there's a vertical asymptote right here, isn't there? You guys see a vertical asymptote? Right? And so can you ever physically make a T shape? No. Right? Because there always has to be some vertical component of the force. Right? That has to add up to the 10 newtons that it's holding up. Okay. Guys got that? All right. The chain gang. So let's call this guy 1 kilogram, 1 kilogram, 1 kilogram. Just make something up. Okay. And let's say the spring scales, I'm just making something up, or let's say their mass individually is like negligible. Right. That top scale is rating about how many newtons of weight? 30, right? That's 10 newtons, 10 newtons, 10 newtons, so it's like 30. Okay. What's the middle scale rating? 20. Right, 20, and the bottom scale is rating like 10. Right. If you made like a whole chain, so like a vertical chain, like a barrel of monkeys, right? Do you guys think that the monkeys near the bottom only have to hold the friends beneath them, and the ones near the top have to hold all their friends? Right? And that plays out in the numbers. You guys should have seen something like that yesterday. If you guys use different masses, that's perfectly fine. Just the top one would have pulled the most weight, no matter what masses you use, right? Right. Oh, how about this? A heavy metal chain suspends a weight at the bottom. Let's say it's old, it's rusty, it's been in a barn since like 1946. What chain in the link is most likely to break first? One near the top, right? Because it has to hold all the weight beneath it. Right? All those links beneath it have weight, right? Right. Hey, what if you slip in a second spring scale here? What's gonna happen? Let's do same numbers. 1 kilogram, 1 kilogram, 1 kilogram. Right. So each of those weighs about 10 newtons individually. Okay. Do you think the top spring scale is holding how much? 30 newtons. What about, let's skip down to the very bottom one. The very bottom one holds how many newtons? 10 newtons. Right. So far that's the same as before, right? Right. Now, before the single middle scale held 20 newtons. What do you think is showing up in these two boxes? 10 and 10. 10 newtons and 10 newtons. Good call. Because the force does split, doesn't it? Force is going to split, distribute, or maybe it was like 8 and 12 or something. But right. It's going to split though, right?
We didn't use all.
All right. One on the back elevator. Oh yeah, I know you guys didn't have time to finish this whole thing, but that's okay. So I know we're a little bit short on time. All right. So if you accelerate this up and down, what happens to the reading? Now it's sort of just the front of the camera right here. I do see this is bouncing up and down. Let me switch to let's go with the red scale. Probably be better. Right. Yeah, I do see here. Oh, sort of simulate this. This is like the reading's bouncing up and down, right? Okay. Now what if it's specifically accelerating upwards? And there's two ways to make it accelerate upwards. Maybe the most obvious way is to start from rest and to pull it up faster and faster and faster. That would be accelerating upwards, right? Okay. Now, if that's the case, like I know if this is hanging at rest, this right here weighs about 10 newtons. but what if I'm pulling up faster, faster, faster? What do you think happens to the reading on the scale? Is it more or less than 10 newtons? It's gonna be more. So that would like increase the scale reading, right? Okay. There was actually a different way to also accelerate it up that what's the other way to accelerate up? If you're not pulling up faster, 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 you could be moving down doing what?
Going slower.
Moving down slower and slower. If you move down to a stop, will the force reading momentarily increase? Yes, it does. Yeah. So that's also that box, right? So 2 ways to accelerate up. Okay. If you guys are ever in an elevator, if you're on the ground floor and you hit up, as soon as you start to move up, you'll feel a little bit heavier just for instantaneously. If you are on the top floor and you're moving down, when you come to a stop, you will also feel heavier moving down, coming to a stop. Okay. Okay. How about accelerating down? Now, the most obvious way to accelerate down is to go down faster and faster and faster. In fact, an extreme version is pure free fall. What if I just like let this go and let it just free fall? What would the scale reading be in pure free fall? 0. It'd feel like it was floating around like an astronaut. In fact, do you guys think that astronauts floating around? They're just in perpetual free fall around the curvature of the Earth. Yeah. So that would be like that, decrease. Okay. The other way to accelerate down, which would probably actually be easier to read, is moving up, doing what? Slowing down. Yeah. So if you move it up to a stop, you guys see that off camera there? As you move it up to a stop, see how it, like the force reading momentarily goes down a little bit. That's it. You see that too, right? Okay. Oh, right. This one hanging over the edge. So if you took some string and tied these together and accelerated this top one horizontally, these two are all like almost the same scenario. They're just like a little bit. This is a variation on this. Okay. Okay. So I got 4 questions here. Let's see if you guys can get these. When the top spring is moving to the left, it's speeding up. That's to say, it's accelerating to the left. What's happening to the force reading? How many of you guys say it's going to increase? So it's going to increase. Yeah, there's my winner. It's right there. It's going to go up. Okay. Do you think it would that would like increase the tension of the string? It's going to increase the values of the spring scales, right? Go up. Okay. How about this? What if you're taking the top spring, you're moving it to the left, so it has leftward velocity, but it's also slowing down. Hey guys, if it has leftward velocity and it's slowing down, that means the acceleration is which way? To the right. Oh yeah, so you're a little bit ahead. You're saying the force reading is going to go down, right? Okay. Yeah, so it'd be accelerating to the right, which means this one would actually be accelerating down, right? This one's accelerating to the right, this one's accelerating down. Even though they're moving to the left, moving up, their velocity is left up, but the acceleration is right and down. Right? And if this one has downward acceleration, it's in partial free fall, which would again match like this situation, right? How about this? If the top spring is moving to the right and speeding up, moving to the right, speeding up, what do you think happens to the force reading? Decrease. Yeah, good call. It would be decrease, right? And finally, what if you're moving to the right but jerking it to a stop? Now what? Gonna go back and increase again, right? Right. So whether the force jumps up or down is related to the direction of the acceleration, but velocity you have to be careful because the velocity could be either direction, but forces and accelerations are always the same direction. Okay. In fact, that's actually sort of a hint to Newton's second law of motion. Right? The acceleration of an object. Why do you think accelerate? Like you guys have been measuring accelerations for last 3 weeks. You guys did a Hot Wheels car rolling, accelerating down the ramp, blah, 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 right? You guys seen that acceleration happens, distances, times, the whole deal. But now we're getting to like why, what causes accelerations? And the answer is forces. Right. Well, from a physics 1 point of view, that would be the case, right? So if you put a force on something, it will cause it to accelerate. If you triple the force, that will triple the acceleration. And these guys always have the same direction. Whatever the direction of the force is the direction of the acceleration. Not necessarily the direction of the velocity. That's a separate concept, right? Friction. All right, now here's where probably tomorrow I want to do a more full version of this, but let's do a quick version right here. So if I lift this, it's reading 10 newtons. So let's say I got a 1 kilogram guy. It takes 10 newtons to lift it. And let's say it drags this across this paper surface. Right? This is reading, now at a constant velocity, it looks like about 3 newtons to drag it, about 3 newtons. Okay. Hey, do you guys see like a ratio of 3 newtons to 10 newtons? Right? 3 newtons to drag, 10 newtons to lift. Right. That ratio has a name in physics. It's called the coefficient of friction. Actually, it's specifically a coefficient of kinetic friction if it's sliding, but just call it coefficient of friction. Okay. So let me write that down. Do some notes here. Okay. So coefficient of I'll say friction for now. Right. If the two surfaces are static relative to each other, you know, like pushing, but it hasn't broken friction yet. Like I'm pushing right now, but it hasn't broken yet. That's called static friction. And once it starts to slide, it goes into kinetic friction. But here, what that ratio is, and that's Greek letter mu. This is I gave you guys remember very first day of school. I gave you guys a stapled packet, right? And on here, I won't point this out to you. You've had this all along, right? It's right here, coefficient of friction. Okay, you guys remember this page way back in the day? Right. So just in case you want to, do I have notes on this? Yeah, we have had notes since the first day of school. That's equal to the ratio of friction force to, technically it's called the normal force. And let me draw a free body diagram to show you exactly what I'm talking about. Okay. So side view, there was the floor. Okay. I took that lab weight. Okay. Here's a little hook, right? Little captain's hook. Spring scale. Right, that was the setup, right? Okay. You know, if I'm dragging that to the right, notice I was dragging at constant velocity when I did that demo. Guys, constant velocity, what is the acceleration for constant velocity? 0. Ah, yeah, you guys got it, right? So, and if there's 0 acceleration, what is the net force? Also 0, right? Right? So here, here's what we're gonna do. Let's do a free body diagram for that scenario. Now I'm thinking of 4 forces on the slab mass. Notice I put a dot right center mass. AP always wants you to do it this way. Put a dot center mass and then draw the force extending from it. We're about to run out of time, aren't we? Okay. So just last few seconds here. Here. Well, I guess I'll let you guys think about this one. So hopefully we'll have time to do this at the lab tomorrow. We're probably not going to be in this room. Actually, we're not going to be in this room. I don't know where we're going to be, but I will put some findings somewhere. Right. So yeah, I think I might see you guys tomorrow. I'll set Proctor in, but you guys have a good rest of your day, and yeah, see you sometime.